So for this reason, we're going to turn into a more advanced model. And this model is going to take into account something called the market price of risk. I'm sure you have heard of it before. Let me try to explain in detail what it is. And with the introduction of this market price of risk, I'm going to be talking about something called Fudge factor. In this world, the expected bond option return is going to be the risk-free rate plus something else. And this something else, I'm going to call it for this class the Fudge factor. And the Fudge factor is going to be equal in general to some lambda, which is the market price of risk times the volatility. And this volatility is going to be the volatility of the bond return. In the next slide, we're going to see how all this comes together. So now, under the local expectation hypothesis, this market price of risk is 0. That means that all bond prices are just basically the discounted expected value. Now, in our Vasicek model, we're going to assume that the market price of risk is lambda v, and where v is from Vasicek. So now what we're going to have is that for all bonds, when you take the expected bond return, you subtract the risk-free rate and you divide by its volatility, then that is going to be equal to a constant lambda. What does this mean? That if, let's say, volatility for another bond is twice as big, then the return minus the risk-free rate must also be twice as big. So the market price of risk puts this notion that when you get more risk, meaning more volatility, you have to get more return. And this is captured by lambda. How are we going to put this into practice? We're going to use a term structure that is not going to assume that we have local expectation hypothesis. So now the price of our bond that we have written as 0D2, for example, is going to be still the discounted value of the expected value of the bond at time t, but now we're going to subtract this Fudge factor. And the Fudge factor is going to be the following function. It's going to depend on the market price of risk, time, and then this difference. These two factors depend on the interest rate of going up and the interest rate of going down. So this factor is the T, D, T plus H. This would be that discount factor. And this other discount factor would be the one that corresponds to the up scenario. Remember that the down discount factor is greater than the up discount factor. And this is what's going to give us our Fudge factor. Now, we're going to assume that the market price of risk for Vasicek is going to be equal to 1/3. And now we're going to value again this 2-year bond at t equals 0. But first we have to compute the Fudge factor. So Fudge factor is going to be 1/6. So it's 1/3 over 2. Square root of 1, since h is equal to 1. And then e to the minus 4.33% minus e to the minus 9.67%. And this is going to be equal to 0.0083. So now in this scenario, the price of the bond is going to be different because now we need to subtract the Fudge factor. So I rewrote exactly the same thing than before, but now I'm going to subtract here the 0.0083. And now the value of a 2-year bond at t equals 0 is going to be equal to 0.8639. Now we're going to do the same thing for the up and the down scenarios. So I copied here the equation as we wrote them before, but we now need to subtract the Fudge factor. So the Fudge factor for the up scenario is going to be 0.0081. And then for the down scenario, it's going to be equal to 0.0085. Then we compute the prices of those 2-year bonds, and we're going to get 0.8238 and 0.9058. So now we got the prices of the 2-year bonds for our tree. So this is done. And now we need to get the prices for the 3-year bond. And remember, for 3 years and up, we need to use the replicating portfolio strategy, the synthetic replication. So I'm putting here the values that changed. All the 2-year bonds changed this price. So this 2-year bond changed its price, this one and this one. And now we have to determine 0D3. How do we do it? By synthetic replication. So replicating here the 0.8238 with N2 units of this bond and N1 units of this one. Then we're going to replicate the 0.9058 with N2 units of the 0.9576 plus 1 unit of N1. And we obtain N1 equals minus 0.671 and N2 equals 1.6465. Then 0D3 will be 0.9324, N1 plus 0.8639, and 2, and this is equal to 0.7968. So overall, the term structure that we get at time t equals 0 is 0R1, the original one was 7%, 0R2 is now 7.32% that you get from the discount factor, and 0R3 that you get from the 0.7968 now equal to 7.57%. What is important here is that we were able, with the Fudge factor, to generate an increasing term structure. So that's the main reason to use this new methodology that incorporates the market price of risk. So the steps that we follow when we don't have local expectation hypotheses are very similar to the ones before. First, we draw the tree for the short rate, like the 0R1, 1R2, and so on. In the second step, we deduce all the discount factors by taking the discounted expected payoff, and then we deduce the zero rates for the two-year rates from these discount factors. Finally, we repeat the steps, but now we are going to use the replicating portfolio, where we equal the up and down scenarios to get the price of like 0D3 and 0D4, and then as we will see in other examples like the 1D4 and a 1D5 and so on. Now, in this term structure where we assume that the local expectation hypothesis doesn't hold, this Fudge factor formula is just an approximation. That is going to become exact when we have very small h. By very small, I mean like 1 week or 1 day. Right now, we're using like 1 year, so this is way too big still. But for academic purposes, it's fine. Now, the second comment is we must use the synthetic replication. This synthetic replication is really important because that's the only way you're going to be able to determine those discount factors for years 3 or higher. Now, in the case that h is small, we're going to have this beautiful equation for our rates. Now here, t is going to be smaller than s, and this future rate. So here you could think, okay, I want the 10-year rate. So the 10-year rate is going to depend on some long-term rate that itself is going to depend on some of the parameters. And then this is going to depend on the short rate, the long-term rate, and then this difference on the maturity, the mean reversion parameter, and so on. Why is this equation important? Because with this equation, you're going to be able to estimate the parameters. These parameters mu, sigma, lambda v, and so on. How can you do it? So there's two ways. The first way is going to be using historical short rate data. I'm not going to give a lot of details. The parameter estimation is not going to be that good, but it can be done that way. And the second way is going to be by using an existing term structure that you currently have. So this is what I'm going to call the rates from the market. So you have a term structure from the market, and then you're going to take the rates from Vasicek, you're going to move these parameters, and you're going to minimize the sum of these squared differences in the rates. And that's how you're going to determine these 4 parameters. Now, of course, you need to have more than 4 observed market rates. You need a term structure with at least like 10, 15 rates to get a good estimate of your parameters. There's some characteristics that your term structure must have to be able to be fit by the Vasicek model. The first one, it needs to be either increasing, decreasing, or flat. The second one, and this is very important, it needs to have a horizontal asymptote. What does that mean? That at some point it needs to flat out, either up or down, but it cannot keep growing forever. It needs to have that asymptote. And the third one is that it must have at most 1 hump. So if it has 2 or 3, then the Vasicek term structure is not going to work. So these would be examples of yield curves that are generated by the Vasicek model. You see here, it's increasing and then it's going to have an asymptote. It's decreasing and an asymptote, and here you see it has 1 hump. So here is the lowest point, and then it starts increasing, and it's also going to have an asymptote. And then the last one is this one that is flat. Now, some examples of yield curves that is not going to fit. So this one has 2 humps, so it's not going to be able to fit it. And this one increases forever, so it's not going to be able to fit any of these 2 term structures. So you have to watch out for that before you decide to use the Vasicek model.